When we think of the ocean's dangers, our minds focus on the monsters patrolling the shallows. We picture massive apex predators, armed with rows of serrated teeth, hunting beneath the crashing waves. We worry about the silent, translucent threats drifting near the coast. These creatures carry enough potent toxins to trigger immediate shock or heart failure from a single brush of their tentacles. Yet these biological terrors occupy a tiny fraction of the water. For centuries, our entire understanding of marine biology has been restricted to this thin, sunlit top layer of the sea. We mapped the surface of Mars in greater detail than the crust of our own planet. Today, roughly 95% of Earth's largest habitat remains a complete unknown to us. This blind spot isn't the result of a lack of interest. We face an invisible, merciless physical barrier. Descending into the ocean is, by many metrics, deadlier than traveling into the empty vacuum of space. As you descend, the sheer mass of water presses inward. For every 10 meters dropped, pressure increases by 1 atmosphere, climbing exponentially. At a few thousand feet down, the weight of dozens of jumbo jets presses on every inch of a vessel's hull. If a hull fails to withstand that force, the result is instantaneous. During the 2023 Titan incident, a structural failure at thousands of feet deep caused a catastrophic implosion, destroying the vessel and its crew in milliseconds. To understand the biology hiding in that 95% void, we have to engineer our way past these crushing physical limits and reach the seafloor. Dropping past the sunlit layer, the water quickly shifts from bright blue to dark gray, and then absolute pitch black. Down here in the mid-water zone, temperatures hover near freezing, and the only light comes from the bioluminescence of the creatures themselves. But this dark expanse isn't completely empty. The seafloor is fractured by tectonic and volcanic activity, pushing up massive underwater mountain ranges known as seamounts. This cross-section shows how seamounts function as deep-sea oases. Ocean currents sweep across the floor, carrying vital organic material. When these currents hit the steep rock faces, it forces them upward, delivering a concentrated stream of nutrients directly to the peaks. Rather than relying on photosynthesis, bizarre ecosystems filter feed from this upwelling. You find ancient coral forests that have lived for over 100 years in the freezing dark, and aggregations of thousands of octopuses nursing their eggs near warm geothermal seeps. Seamounts prove that biology can adapt to extreme darkness. But if you leave the mountains and descend further to the flat abyssal plains, the ocean hides a secret that challenges our basic understanding of chemistry. 13,000 feet down sits the Clarion-Clipperton Zone, a massive, flat, and muddy stretch of the Pacific abyssal plain. Here, scientists detected a major anomaly. Sensors picked up increasing levels of oxygen near the seafloor. This directly contradicted a core rule of biology, that oxygen requires plants, algae, and sunlight to be produced. Down here, there is zero sunlight. The source of this oxygen turned out to be millions of dark, potato-sized rocks scattered across the mud, known as polymetallic nodules. This illustrates how the nodules function. Containing layered metals like manganese and iron oxide, they act as natural batteries. When clustered in saltwater, they generate an electrical charge. This triggers electrolysis, splitting H2O molecules and releasing oxygen gas into the water. This reaction demonstrates that the deep ocean can generate its own life-sustaining atmosphere, operating entirely independent of the sun. If we continue the plunge into the Hadal Zone, reaching the 36,000-foot depths of the Mariana Trench, the pressure hits 1,000 times that of the surface. Life persists even here. Extremophiles dominate the crushing void, from giant scavenging amphipods that tear apart biological debris to xenophyophores, massive single-celled organisms that grow up to 20 centimeters across in the toxic mud. The energy fueling these regions often comes from hydrothermal vents, underwater volcanoes spewing a 400-degree chemical soup. Biologists suspect this unique combination of extreme heat, water, and rich chemistry provided the spark for the very first living cells on Earth. Because the conditions are so extreme, space agencies like NASA send astronauts to live in underwater laboratories like the Aquariuspace. They are preparing to search for extraterrestrial life in similar saltwater oceans hidden beneath the icy crust of Jupiter's moon Europa. These hostile trenches function as active biological laboratories. They provide a living record of how chemistry transitioned into biology in the most extreme conditions on our planet. But there is a disturbing catch to this scientific frontier. Human environmental impact has vastly outpaced human exploration. Even in the most remote trenches, robotic submersibles are touching down only to find man-made trash and plastic wrappers resting in the ancient mud. This cross-section shows the mechanics of the contamination. Surface microplastics and industrial chemicals, like PCBs, slowly sink. Over time, the ocean currents funnel and concentrate these pollutants down into the deep V-shape of the trenches, contaminating the very extremophiles living 36,000 feet below. We are leaving a heavy chemical footprint across the ocean floor, thoroughly saturating an environment before our scientists ever had the chance to study it. Now, an even larger threat is mobilizing. A multi-trillion-dollar deep-sea mining industry is actively deploying massive industrial ships to target the abyssal plains. Their primary targets are the exact same polymetallic nodules that generate the deep sea's electrical charge and produce its oxygen. The process of blindly dredging these nodules from the mud will instantly obliterate ecosystems that took millions of years to form. Studies of past test mining sites show that these deepwater environments simply do not recover in our lifetimes. The deep ocean contains a unique record of our biological origins and a physical template for the environments we expect to find on icy moons like Europa. Human industrialization threatens to dismantle this alien world before we even have the chance to complete our search.